Então, boa tarde a todos. Bem-vindos ao ciclo de seminários do Departamento de Estatística da UFMG. Então, hoje vamos começar com o primeiro seminário e eu vou fazer a introdução em inglês para o professor Simon poder... não sei se ele está entendendo um pouco de português, mas vou tentar falar em inglês aqui para fazer a introdução dele, para que ele compreenda também. So it's a pleasure to have here with us today Simon Lunagomez. So Simon is an associate professor in statistics in the Department of Statistics at the ITAM, Instituto Tecnológico Autônomo de México, in Mexico City, right? So talking a little bit about his academic path, so Simon got his bachelor degree in actuarial science from Universidad Nacional Autónoma de México. Also a Master of Science degree in statistics from Universidad de Guanajuato in CIMAT, right, in Mexico. And a PhD in statistics from Duke University. Basically, we had an intersection during our PhD period at Duke University, so that's where I met Simon. And between the master's and PhD degree, he had an experience as a statistical analyst at the MD Anderson Cancer Center in Texas, right? And also a postdoc position after his PhD in statistics, a postdoc position at Harvard, and also a research associate position at the University College London in the United Kingdom, and also a lecturer position at the Lancaster University in United Kingdom. So since January 2022, he works at ITAM back in Mexico. And in terms of research interests, so he works with social networks, graphical models, applications of computational geometry and computational topology to statistics and shape theory. So Simon, thank you very much for accepting my invitation to be here with us in our academic seminar today. So you may start.
Oh, thanks, Vinicius. Thanks for the kind introduction. I want to thank everybody who's listening for coming to the talk. Let's get started. So today I'm going to talk about Bayesian modeling for hypergraph data. This was the main paper or main work for one of my PhD students' doctoral thesis. This was Catherine Turnbull, who's in the UK. This was joint work with Christopher Nemeth, who was the co-supervisor, and Eduardo Eroldi, who's at Temple University. You can move to the next slide. Okay, so I'm going to talk about networks, which you can also call relational data, where you have objects or people, and you have relationships between those objects or people, and you have measurements at the level of the objects, and you have measurements at the level of the relationships, okay? So most of the literature focuses on the case where the relationships only comprehend two of the objects at a time, okay? So for example, you can have Facebook friendships, someone following someone on Twitter, or the transmission of a disease. Someone transmits the disease from person A to person B, okay? So that type of data sets are usually represented by a graph. So that's the figure we're looking at the slide. So here the objects are going to be academics in the UK, and the edges represent collaborations. Okay, so that's one type. No, don't touch this slide yet.
Sorry.
Okay, so don't worry. So that's one type of relational data. But we're going to focus on a different type of relational data where we can have higher order interactions. For example, co-authorship of academic papers. So you can have an academic paper, and you can see it as a relationship between the authors, and you can have 3, 4, or more authors involved. Okay, now we can move to the next slide. So then these objects are called, the objects that we use to model the situation are called hypergraphs. And again, they have a set of objects that are related. We're going to call them nodes. And they're going to have hyperedges, which are subsets of this set of nodes. For example, in this figure, we have on the left a set of 5 nodes, and then we have subsets. And these subsets, 1 of 3, 1 of 2, and 1 of 1, those can be the hyperedges, okay? So that's one way of representing a hypergraph. The other way of representing it, which is universal, is to think of a bipartite graph, where you have on one side of your bipartite graph, you have the nodes, and on the other side, you have the hyperedges, okay? So this representation, as I said, is universal. And you could say, okay, why bother studying hypergraphs if you can always reduce it to a bipartite graph? The problems are that here you're gonna have a random number of hyperedges. So that's gonna be a bit hard to incorporate in a model. And the other thing is that you may have assumptions of how your graph is connected, your hypergraph is connected. And it's tough to incorporate those assumptions if you use a representation like the one you have on the right. So we're not gonna follow that path. Vinicius, you can. Excuse me, as I said. Thank you. So we have literature for modeling hypergraph data. Is way less developed than the literature we have for graph data. And what happens is usually authors take as a starting point a well-developed model for graphs, and then they generalize it for hypergraphs. For example, you have the Ergon model, in which you have the probability of observing a given graph, and then you see it as a regression with respect to features you would like to see, like number of stars, number of edges, number of triangles, etc. So that can be generalized to the hypergraph setting. That was done by Stasi. You have the stochastic block model, which basically is based on modeling the communities or sets of nodes that are highly connected with respect to other subset of nodes. And this was generalized to the hypergraph setting by Kostadidar. Then you have professional attachment, where a mixed membership model, where you can have communities, but you can belong to more than one community at a time. For example, you can belong to your school, but you can also belong to a syndicate. You can also belong to a sports club, etc. So the communities overlap. Okay, so this was done by Liu. And finally, there is a model based on clustering that was developed by Ng and Murphy. So there is a very important class of models for networks called the latent space model, which was developed by Hoff and Raftery. And there has been not much development in generalizing this model to hypergraphs, and this model has many desirable properties. One of them is called transitivity. Transitivity formalizes the idea that the friend of your friend is going to be my friend, okay? And also, latent space modeling allows us to have a flexible modeling for what's called motifs, which, for example, are triangles, stars, and other subgraphs. Okay, Vinicius, you can. Okay, so I'm going to talk a little bit about this latent space approach. And what we do is we take our nodes or objects we want to model, and then for each of them, we represent it as a latent position in Rn, okay? So we want to denote each of these latent positions by U sub I. And then we're going to have a set of indicators. This is going to be denoted by Yij. And these indicators are going to be 1 if there is a relationship or edge between I and J, okay? So now, the idea that Hoff and Raftery developed was to say, okay, let's regress this with a regression model for the indicator of a relationship with respect to the latent positions. And here we're looking at it. It's a generalized linear model. So basically, the closer to latent positions are, the more likely is that there is going to be a relationship between the corresponding nodes. And this model has many cellular properties, which are very well explained in the bibliography in the monograph by Rastelli. You can move to the next slide. Okay, so what's the idea of our paper? The idea of our paper is to combine this model, the latent space model, with a construction that has a more geometric flavor in order to model hypergraphs. So we go step by step. We start with a construction that allows us to construct graphs first. So we take the latent positions, and then for each latent positions, we're gonna surround it with a disk. Okay, all the disks have the same radius. Okay, so we're gonna look at the pairwise intersections of these disks. You can go to the next slide. Okay, so if a pairwise intersection is non-empty, then I'm gonna say that the indicator for an edge for that pair is gonna be 1. Okay, so this is what we have here. We have these 7 disks, and we have, for example, between 2 and 4, there is a non-empty intersection between the disks, and then we draw an edge. Okay, and then we do the same for each possible pair of latent positions. Okay, so this object is called a random geometric graph, essentially because the layout of the latent positions come from a distribution. Okay, now let's go to the next slide. So there is a generalization of the idea of geometric graph. This is called the check complex. Essentially, we're gonna take the latent positions. Again, we surround each latent position with a disk, and then we're gonna look at the possible hyperedges of different orders. Order is the number of nodes that are involved, and we're gonna say that a given hyperedge is present, or the indicator is equal to 1, if the corresponding simultaneous intersection of the disks is not empty. For example, here we have 2 and 4 intersect, and there's going to be an edge. We have 3, 6, and 5. They intersect as pairs, but they also intersect as a triad. The disks intersect at the same time. So if I take the indicator of the presence of the hyperedge 3, 6, and 5, that's going to be 1. Let's go to the next slide. So this is the object we obtain at the end. It has edges, but it also has higher order relationships, which is the triangle that is shaded. Okay, so have we finished? No, I mean there's a lot that needs to be improved from this construction in order to come up with a model that models what we want to model, and it's tractable from a statistical perspective. Let's go to the next slide. One limitation of this model, the main limitation, is that it only allows you to generate what's called simplicial hypergraphs. That's one way to call it from a statistical perspective, or simplicial complexes, if you are familiar with the literature in topology or computational topology. So in a simplicial complex, what happens is you have a relationship of certain order, but then for it to exist, all the relationships of lower orders need to exist. Okay, so for example, in the previous figure, we have a 3-order relationship, but that existed because all the pairs were there. So that's too restrictive, because let's say we want to model a co-authorship data set, and then what can happen is you can have 3 authors, and yes, they can write a paper, the 3 of them together, but that doesn't imply that we need to have all the pairs of authors writing papers together. Okay, so this is so the figures show these examples that we want to be flexible enough to generate hypergraphs of this sort. Let's move to the next slide. Okay, so how do we solve that problem? The solution is very simple. So what we're going to do is we're going to condition on the latent positions. We're going to keep them fixed, but we're going to have a collection of radii. One radii per order of hyperedges that we want. And this sequence is going to be increasing. So the higher the order we want, the higher the radii. So for example, let's say we only want relationships of order 2 and 3. So we're going to have to pick then 2 radii, where 3 is larger than 2, and then use the intersection, the pairwise intersections from the balls in blue, from the smaller radii, to generate the pairwise relationships, and then the intersection pattern from the balls in purple in order to generate the 3-order relationships, okay? So let's move to the next slide. So this is the object that we generate by doing this. So again, we have pairs, we have triads, but we observe that this hypergraph is not a simplicial complex. Why? Because we have the relationship 3, 6, 5, but we don't have all the possible pairs. We don't need all the possible pairs for this relationship to exist. Okay, let's move to the next slide. Okay, so this is the difference between the non-simplicial hypergraph and the simplicial complex. So this is the first construction only could generate what's on the right, but now we can generate things that are on the left. Let's go to the next slide. Okay, it's very important that we keep the radii increasing, because if we don't follow that constraint strictly, what we're going to end up generating is going to be a simplicial hypergraph. Okay, let's move to the next slide. Okay, so one question we ask is, okay, are we done yet? Do we already have the model that we want? And the answer is not yet. So this is because 2 reasons. The first one is that it's very hard to describe the support of the distribution on hypergraph space that we have constructed based on this model. Okay, so do we generate all possible hypergraphs with this model? Not likely. One of the constraints is, for example, the generation of star graphs, and this has to do with geometrical constraints called the kissing number. Okay, so we cannot generate very high order of star graphs. This has to do with the geometry of the ball and with the geometry of Rn. Okay, so the support is constrained somehow. And then what happened is that given the latent positions, the construction of the hypergraph, as I have explained, is deterministic. Okay, so if you want to write your conditional distribution, you're going to have a series of indicators, the product of a lot of indicators, and then either you get everything right from the hypergraph you generate with your latent positions with respect to the hypergraph you observe, or you get at least one thing wrong, and then your likelihood is that conditional distribution is going to become 0. So it's going to be very hard to do computations because you have to get everything right in order to have a non-zero conditional distribution. So there is one way to get around both challenges, and this is the following. Let's generate the hypergraph as I described before, but then once we have the indicators, all of them, the ones that are present and the ones that tell you that the hyperedge is absent, and then contaminate them with a very small Bernoulli noise. By doing that, you turn your support into the whole space of hypergraphs of the order you want, and then you have a very nice conditional distribution that connects the latent positions with the hypergraph you observe. We can go to the next slide. So what's our generative model? Now, this is the model we want. We're going to generate the latent positions from a distribution. We're going to use the bivariate normal or normal in 3 dimensions. This is to follow the construction by Ratter and Hoff, but we could use a different distribution. And now for the hyperedges of different orders, first we construct the series of balls with a given radii, and we look at the intersection patterns as I explained before. But now, for each of them, we're going to use a Bernoulli noise, and the Bernoulli noise depends on the order. The probability of perturbing depends on the order of the hyperedges, and then we contaminate all those indicators. Okay, and that's our generative model. We can move to the next slide. Now, that's the model. How can we perform inference? Well, it's going to be via MCMC, and we can do this via a Gibbs sampler with metropolis steps. Okay, so it's not very complex. Now we're going to denote by D, G, and K, comma, H, and K the difference between the hypergraph generated by the latent positions and the hypergraph that we observe. So this distance, if you're familiar with metrics theory, is called the Hamming distance. So basically it tells us the number of mismatches between two objects. And then the conditional distribution between the graph that is generated by our model and the graph that we observe is given by this distribution, which has this set of discrepancies and the probability of perturbing the hypergraph generated by the deterministic method. So that's a very friendly distribution to work with when we code our MCMC. We can move to the next slide. Now, one thing that happens with one issue that happens with the latent space model is that a lot of times it's very hard to scale it up. So we have to be careful and try to improve the computation in as many ways as we can. Okay, so to scale it up, we use for the latent positions, we use what's called a delayed acceptance scheme. And basically, when we update each latent position, we ask ourselves, okay, how much are we messing up in terms of the connections we're doing in a given order? Let's say you start with order 2 with respect to the graph that we observe, the hypergraph that we observe. So we first test how much we're messing it up with the interaction of number 2, and then we can get rid of very bad proposals for the latent position. And then we go to the intersection of order 3 and so on. So that way we can get rid of bad moves and rank or these delays according to computational complexity. Okay. Now the other way we implemented to improve the computational efficiency for model is the following. So you see that in this case the probability of having an edge or a hyperedge depends on the relative distances of the point pattern with one respect to the other. So if we rotate it, translate it, or reflect it, we still have the same interaction. So our model is non-identifiable. So what Rafter and Hoff did, and what a lot of people do, is they do procrustis analysis. So they perform this computation per iteration of the MCMC. So we found that very bothersome. So what we did is we used what's called the Bookstein coordinates in order to perform the computation only once, and then move in this space, which is going to be a quotient space, and get rid of all those transformations. I mean, all the translations, rotations, reflections, and scaling are going to be taken into account in this space. We can go to the next slide. Thanks, Milish. So this is something this technology we borrow from shape theory, the Bookstein coordinates. And basically what we do is we take 2 points from our configuration of points. We call them anchor points. And then these points fix in terms of rotation and translation. Now, because the distance of these points is fixed, is also fixed in terms of scaling. So that makes the radii that we're going to use later, it makes it identifiable. Okay. Now, if we constrain a third point to be on the upper half of the plane, then what's going to happen is we're going to get rid of reflections as well. We don't do that. It's very hard to get problem non-identifiability in terms of reflections, especially when you have many vertices or latent positions. So that's not necessary. So we define this space beforehand. We choose the anchor points, and basically we update in these coordinates, and then that reduces a lot the computation burden. We can keep on. Now, you may ask, how do we know that the intersection of a number of disks is not empty? That sounds computationally bothersome. It's not. This is a well-studied problem in computational geometry, and it's solved by a technique called the mini-ball algorithm. What mini-ball does is says, okay, the problem of determining that the intersection of a series of balls is not empty is the same as the problem of encountering the radii, let's call it R star, of the disk that encompasses the centers of the balls. So that algorithm is very efficient. It's described in the monograph by Edelsborn and Harrer of computational topology, or the monograph on computational geometry by Overmars. So it's very well, and it's implemented in a library called Goody. So we don't have to worry about that. Let's go to the next slide. Okay, so let's start playing with our model, and let's do some simulations. So here we have 50 nodes, and we're gonna consider relationships of order 2 and 3. Okay, and then what we're gonna do is we fit our model, and then we have the posterior paths of the latent positions. That's what's on the left. Okay, so I think you can see the anchor points. It's a little dot that is pink, and it's a little dot that is blue on the x-axis on the height of 0. Okay, so those are the anchor points. So those don't move, and everything else is relative. All the positions are relative to that. Now, if we take the posterior mode of each of the latent positions, and then we compute the hypergraph that we will obtain with the radii, then we have the figure on the right. Okay, so this is what we're going to do, and this is one type of inference you are interested in. Imagine you are talking about co-authorship. So this is a set of established authors, and we have their collaborations or papers that they write together, and we're going to introduce a new series of authors, and we want to predict how this new set of authors is going to interact with the established ones. Okay, so that's we incorporate that in the simulation by saying, okay, we have these 50 nodes. Let's play with let's add another 10 nodes, and let's predict how we connect. So let's go to the next slide. So we do this in terms of the degree distribution. The degree distribution is you have each individual, and you ask them how many relationships you have. And then you have relationships of order 2 and relationships of order 3. And here for each of the simulated data sets, we see that we see the comparison between the degree distribution of the one that is observed, the one that is real degree distribution, versus the one that is predicted by our model. And we found that for order 2, it behaves pretty well. For order 3, it's a bit harder, but the predictions look reasonable. Okay, let's go to the next slide. So we play with 2 data sets. The first data set was analyzed by Ng and Murphy for the hypergraph model, and here we have the strip of Star Wars in the New Hope, and then we see if two of the characters appear in the same scene, okay? 2 or 3 of them, or 4 characters appear on the same scene. Now we're gonna get rid of the repeated edges or hyper edges, and we're gonna consider relationships up to more than 4, okay? So what we want to do here is to fit our model and predict the degree distribution of all these characters. So we can move to the next slide. Now we predict the degree distribution of Luke Skywalker and the one of Darth Vader, and we found that for 2 and 3, it's very it worked well, but for order 4 it was a bit noisier. So that was our insight from it. And this can be seen in the first version of the paper, which is on arXiv. So you can see a detailed explanation of this example. Vinicius, we can turn the slide. So now let's talk about co-authorship. And here we have 99 statisticians, and the colored pattern that you see represent the hyper edges, or the fact that they collaborated in an article for the top 5 statistical journals. Okay, so that's the data we're gonna try to analyze. Now you can move to the next slide, please. So this is not the whole data set. This was discussed by Mao and his co-authors in this paper, which is much lighter. It's several hundred authors. But for the sake of illustration, also because of the limitations of the scaling of our model, we subsample 99 of these authors. We use an algorithm called Snowball to subsample them. Basically, we start with one node and then we take all the neighbors, all the neighbors, all the neighbors, and so on until we reach 99. And we only consider relationships up to order 4. Now, we can do that. We can visualize the hypergraph, but then we can keep sampling using Snowball and look at an additional subset of 10 nodes, okay? And now we want to predict the relationships of these 10 new nodes on these 10 new authors with respect to the 99 we had originally. Okay, move to the next slide. So what do we want to predict? We want to predict the degree distribution again for order 2, 3, and 4. And here the plot is from a newer version of the paper. So now we took care of the following. We are not plotting the degree distribution, but the difference of the observed and the predicted. Okay, so they collapse to 0. So that's good. We also try to predict motifs. So this is the presence of triangles that are incident to the nodes. Also hyper edges of size 3 and 4 and so on. So that's what's on the bottom. And this example is also explained in detail in the new version of the paper. So we can move to the next slide. Okay, so what have we done? We have presented a novel model for hypergraph data, and this model uses advantages from computational topology, and basically the idea that part of the structure of the model can be burdened into a construction that has a geometric flavor and is deterministic. Okay, so now this approach can be modified in different ways. We use the normal distribution in order to model the layout of the points, but you could follow an approach like the one proposed by Penrose for random geometric graphs and use a point process, for example. So that's something we would like to explore. So you can play with different distributions for the layout. You could also play with the sets that you use for computing intersection pattern. So you can use the generalization of what's called a check complex, which is called a nerve. So that will entail, if you use different sets, you impose different constraints on the graph that's generating, and then it might be you may get different distributions. And there are several generalizations of the latent space approach, and we would like to incorporate some of them. For example, you can make it dynamic. That would be interesting to have a dynamic hypergraph. So that's what I wanted to share with you. Thanks so much for listening. Let me know if you have any questions.
Okay, Simon, thank you for your presentation. Quite interesting. I have a few questions. If any student want to ask questions, please, you can type your question, even in Portuguese. I can translate in the chat. So before people do that, I will make my questions. So basically, I was wondering, how do you choose those anchor points? I can go back here to the for example, here
in principle, it shouldn't matter which pair you choose. So basically, you say, I'm gonna take these two individuals, and then I'm gonna pick their respective latent positions, and then I'm gonna decrete that those are my anchor points. So they're gonna be updating everything else relative to these two, but it shouldn't matter.
Okay, so it doesn't matter if they are close to each other or far away from each other.
Yeah, because closeness here is an artifact of the fact that you are embedding them in a rank. So it doesn't have to do with the actual fact that there's a relationship or not.
Okay, and also I guess in slide 13 here, you talked about this distance of number of mismatched. How is the magnitude of this? Is like a proportion? You are looking of number of matches and divided by the number of possible connections. How is this distance?
No, it's just an absolute number. So if you have two graphs, and you basically you look at what's called the adjacency matrix, which is a set of indicators, and you basically say, okay, how many discrepancies are in terms of zeros and ones, and that's it. And then you can generalize that to a tensor when you are looking at the higher order relationship. So the thing is, like, we take advantage of the fact that there is a simplicial complex underlying some of these constructions in order to not deal with the tensor and compute these distances.
I was wondering whether the size of the graph would impact on this distance, but in this case, because if you have if you take the number of mismatches, this could be a small or a large number, right?
Yeah, it's only XOR operator. It's a XOR operator, and the thing is, you have to figure out how to write it when you have higher order relationships, so you don't deal with the tensor. So basically, you can get rid of a large part of the space.
Okay. And also, when you define your model, you talked about this the circles and also intersections. Is there another way of establishing this, like rather than using circles and intersections? I don't know, perhaps distances and some threshold or something like that. I'm not sure if people have thought about doing something different in the literature.
That's a very good question. I think you can use different sets than balls. So the theory of computational topology does that. They have this general idea of a nerve, which essentially you have a series of sets. They're usually convex, but they don't have to be. And then you look at you compute the intersection pattern of them. So we use balls because they are simple to understand, and we have mini ball algorithm, which is easier to compute. But there are other technologies for using different sets. But basically, what I will advise, or if you want to pursue the direction, is first check what type of technology is available in the computational topology literature for computing the intersection pattern. Because one thing is what you can conceive, and the other thing which is computationally feasible.
Okay. And in the beginning of your talk, you mentioned some the slides here, like a current methodology. Have you tried to compare anything, any result you get from your model to other possible competitors?
You know, this is the type of question you get from a reviewer, but the reviewer did not ask us to do that. So basically, we're in the stage of minor corrections, and because they haven't asked us to do it, we haven't done it. But it will be interesting to maybe for a master's thesis or something like that to do a comparison of different approaches. And I think the reason why we haven't done that is maybe because they focus on different types of inference. And at the time we started, that was one. And the other one is when we started, some of these models were proposed, but there was no inferential approach added in the paper. So they say, okay, we have this model for hypergraphs. For example, Stasi. When we read or when that version of the paper was up, when we were working, only the model was presented. Now they have an inferential approach. So now you could compare. So
okay. Okay, so looking at the chat, no students is asking questions. They are quite shy to write questions in English. So I guess that's all I have to ask. So we can now move to the end of our presentation. And basically, I would like to thank you, Simon, for your time, for preparing this talk and to be here with us today in our academic seminar. Thank you very much. I will end the broadcast, and so this video will be available in our YouTube channel. So if anyone wants to check the details later, so anyone can see from our channel, Simon allowed us to keep the video. So stay a little bit here. We'll just end the broadcast and then I talk to you, okay?
Okay, so it's been a pleasure. Thanks so much for the people that attended the talk. Thanks to you, Vinicius.
Ok, so na próxima semana nós temos mais um seminário que vai ser presencial, pessoal. Então até o próximo.